Welcome all on the video tutorial in machine learning. Today we are going to discuss about the fourth module, and under fourth module we are going to discuss third session, which is ML and LS error hypothesis. We'll see what is ML and LS hypothesis and what is the relationship we have between both the things. See, ML is nothing but maximum likelihood condition. Okay, what is maximum likelihood condition? And LS is nothing but least squared error hypothesis. What is the relationship we have with ML and least squared error hypothesis? We'll discuss. First, we'll know what is maximum likelihood hypothesis. Okay, what is likelihood hypothesis? Likelihood hypothesis is nothing but the expected hypothesis to occur. Okay, for example, when I toss a coin, I am tossing a coin and I expect the result of tossed coin to be an head. That is my likelihood hypothesis. The expected output, the probability of the occurrence of the expected output, you say it as likelihood hypothesis. Then what is maximum likelihood hypothesis? At the given instance, what is the maximum number of likelihood condition occurs? For example, for the instance, when I toss a coin 10 times and for all my 10 times I expect the outcome to be a head, and the number of times the head has occurred is your maximum likelihood. What is the maximum number of time that a head has occurred? That will be your maximum likelihood condition. And the concept here, what they are trying to say is that whenever you have a least squared error, when you minimize your square error, least square error, then you can obviously increase your maximum likelihood hypothesis. That is the concept behind this topic. Okay, what they are specifying in this topic, whenever you minimize your error, the probability of your maximum likelihood will be higher. Okay, and it is vice versa. When you have you have more errors, then the occurrence of maximum likelihood condition will be less. And this significant they have used for Bayesian justification for implementing that in the neural network. Okay, we use many of our learning approaches are using neural network learning, linear regression, and polynomial curve fitting for learning the continuous value target function. We know that. Okay, and now what we implement is that we are trying to implement the concept of when you have a learning algorithm which is going to minimize the square error between the output hypothesis prediction and the training data. With the training data, when you have the minimal error of output prediction, when you minimize that, that is going to give you the output with the higher likelihood condition, that is the maximum likelihood condition. So you are going to implement this significance under an Bayesian rule. Okay, we are going to follow the Bayesian rule for achieving this condition. Okay, in order to find the maximum likelihood condition using a Bayesian learning, and we'll be using this for an continuous value target function, we are starting with maximum likelihood hypothesis, and we give a definition here, and we choose a case P for referring the probability density function, and we use the formula hypothesis of ML, that is a maximum likelihood condition you derive from the argmax of H given the instance. Okay, H given the hypothesis with the probability density function D given H. P is the P refers to the probability density function with the respect to the D given H. Okay, and D is your target value and H will be your hypothesis. So you, for the specified target value, what is the hypothesis, you will be defining that to the argmax in the given instance. Okay, and you rewrite this formula using the product rule. Hypothesis of ML will be your argmax, H given the hypothesis from the input vector from the lower level I is equal to 1 to the upper limit, from the lower limit I is equal to 1 to the upper limit m, and we are going to find the density function, that is the probability of density function through P of di, that is the target value given the hypothesis. Now we use logarithmic value for the simplification process, and we use the logarithmic function for deriving like maximum likelihood, hypothesis of maximum likelihood by the formula argmax h given the hypothesis, and the logarithmic function from the lower limit I is equal to 1 to m with 1 divided by square root of, so since it is least square, you're using the square root of 2 to the pi sigma square multiplied with the e of minus 1 by 2 to the sigma square and a density of minus u the whole square, and you simplify this further, it is simplified by argmax h given the hypothesis and the lower limit I is equal to 1 to m, 1 by square of 2 to the pi sigma square multiplied with that hypothesis. Now we are going to apply a transformation for achieving the maximum likelihood calculation. Again we use a logarithmic value for making our calculation easier. We implement the logarithmic function and we discard the constant in each and every step from the derivation. The first we obtain h of hypothesis of ML, maximum likelihood will be the argmax h given the hypothesis, summation of I is equal to 1 to the m with the logarithmic value you are using for simplification process, 1 by square root of 2 pi sigma square minus 1 by 2 to the sigma square di h of xi the whole square, and in the first you are discarding the constant. So when you discard the constant you get hypothesis of ML will be argmax h given h, and the summation of I equal to 1 to the m, 1 by minus 1 by 2 to the sigma square di minus h of xi the whole square. When you discard the or the negativity, again whenever you are maximizing the negativity continuity, this will be in turn reflected by maximizing your positive quantity. Whenever you reduce your whenever you reduce the negative quantity, when you reduce the errors, that will be helping you to achieve the higher maximum likelihood condition. So when your errors are less, your likelihood condition will be, the probability of occurrence of a likelihood condition will be higher. That is what the concept you have here. Whenever you reduce your error, whenever you diminish your error, it will help you in the higher maximum likelihood condition. The probability of occurrence of maximum likelihood condition will be high when your errors has been reduced. How do you determine the error? Whenever you have a deviation between the obtained output and the actual output. Suppose what is this supposed output you are supposed to get, actual output you are supposed to get, and you have a difference of that. When you have a variance with that of your actual output and your obtained output, it specifies the error. Okay, you have error mechanism and you will be implementing the back propagation algorithm to minimize your error. Okay, so whenever you have the higher probability of error, you have lesser maximum likelihood condition. Whenever you have less probability of error, okay, when your errors are less, in turn your maximum likelihood condition will be higher. Okay, so each and every chance when my error gets reduced, again my chance of predicting the hypothesis gets higher. How do you reduce the error? By training it with the higher number of data sets. When your machine is trained with more data set, then the probability of error, your prediction rate will be accurate comparatively with that of when you go with training of lower data sets. So when you train a machine with higher data set, it in turn it helps you to reduce the error. When your errors reduce, your probability of maximum likelihood condition increases. This is what the concept about maximum likelihood and least square error hypothesis. Whenever your squares are minimized, your maximum likelihood condition, the probability of occurrence of maximum likelihood conditions will be increased. That's all for today's session. Thank you all.